Hi, I'm Aniruddh from USC and I will be presenting our work on learning from demonstrations using Signal Temporal Logic. Learning from demonstrations, or LFD, is a paradigm for learning robot control policies from user demonstrations that does not require explicit programming for each task. Demonstrations inherently define expected robot behaviors. In our work, we plan to learn such behaviors in terms of rewards that can be used by reinforcement learning algorithms to extract robust policies. The motivation of our work is to propose a framework for LFD that has the following features: defining metrics to evaluate and rank the quality of demonstrations, to learn from few demonstrations, is applicable to non-expert users who lack the skill to provide optimal demonstrations, and finally, to learn rewards based on state visitation history in the demonstrations. The key idea is to use formal logic and its semantics with LFD. We use a flavor of temporal logic called Signal Temporal Logic, or STL, to formally define robotic tasks. The quantitative semantics or robustness of STL is used to automatically evaluate and rank the quality of demonstrations, hence facilitating learning from imperfect demonstrations. The temporal aspect of STL allows us to infer non-Markovian rewards and specify safety conditions in a very intuitive or logical manner to learn robust control policies. The problem that we are trying to solve is, given a transition system with unknown rewards and dynamics, a set of STL specifications, and a set of user demonstrations on a particular task or environment, the objective is to infer rewards for the transition system so that the policy learned via the reinforcement learning algorithm satisfies those specifications. We now briefly describe our methodology. Consider a grid world setup in which an agent needs to learn a policy from the start to the goal while avoiding obstacles. The STL specifications for this environment are logical representations of the task objectives, that is, reaching the goal and avoiding obstacles. A set of user demonstrations for this task are provided. The STL formulas are first categorized into hard and soft specifications and then arranged in a directed acyclic graph to encode dependencies. Based on the evaluation of a demonstration with respect to the task STL, we obtain two types: a good demonstration in which every state satisfies all hard requirements, and a bad demonstration in which at least one state violates a hard requirement as shown. Each formula is represented as a node in a directed acyclic graph and is assigned a weight based on the number of its dependencies, hence creating relative importances among specifications. The total robustness of each demonstration is a linear combination of its individual robustness with respect to each specification. To assign rewards, for every good demonstration, the reward at each step is a cumulative fraction of its total robustness. And for every bad demonstration, the reward is assigned to states that violate the hard specifications. All other states not seen in the demonstrations are assigned 0, that is, we are neutral to the states and do not make any assumptions. Finally, the rewards are normalized and scaled. The demonstrations are then sorted by their quality to obtain a ranking, and the final reward is a linear combination of the ranking and total robustness of each demonstration. Thus, using formal specifications help to learn from imperfect demonstrations. The inferred rewards help to generate policies that satisfy the given STL requirements and learn user preferences. We compare our method with the state-of-the-art inverse reinforcement learning algorithm that inevitably requires all optimal demonstrations. The results show that our method outperforms MCE-IRL in terms of the number of demonstrations required and on the quality of rewards learned. In addition, our method can even learn from suboptimal demonstrations. The table shows more comparisons for different environments for the number of demonstrations required and average time taken to extract rewards. To summarize, we use formal specifications to define tasks, evaluate the quality of demonstrations based on the task, and infer rewards for robust and interpretable control policies. Thank you very much, and we are open to any questions.